thank you so much for joining me once again. I hope you're all having a wonderful Halloween weekend. So let's get into today's topic. So today, what I want to talk about is the notion of the power set. So what is that? A power set of a set is the set of all its subsets. Kind of a tongue twister, but I think the idea should become pretty clear as we go through a few examples. So let's get started, and as always, if you like this video, press like and subscribe, and let me know in the comments what other topics I should cover in these videos. So let's get started.
So hopefully we all remember what this expression means. It means A is a subset of B. It means every element of A is also an element of B. Or if we're talking about it in geometric terms, A is wholly contained within B. So crucially, A is a subset of B means something very different from A is an element of B. Here we're saying all the elements in A are also elements of B, but here we're saying that A is one of the elements of B. These two expressions mean very different things. They're not the same. However, we can subtly manipulate this expression A is an element of B, so it does mean the same thing as A is a subset of B. So all we need to do is add this curly P symbol. So it looks like a P, but it's just a bit fancier, a bit curlier, right? So something like that. So all we did to change this expression is we added this curly P symbol. So let's look at what that would look like. So here we go. We've updated this expression by adding this curly P symbol. This one here. This symbol is the power set symbol, power set. So what we're saying here is A is an element of the power set of B. Okay, so now we've updated it. Now we've updated this expression. These two expressions do mean exactly the same thing. So A is a subset of B is just another way of saying that A is an element of the power set of B. And A is an element of the power set of B is just another way of saying A is a subset of B. So they mean exactly the same thing. All we did was we changed the subset symbol to this element of symbol, and we added the power set symbol around B. Let's look in a bit more detail about what this power set symbol actually means, how to define it, and how to use it. So let's look at the definition. So a power set. So let A be a set. So A is just any set. The power set of A, so the curly P symbol is the power set symbol. The power set of A is the set of all subsets of A. So the power set of A is also a set, right? So that's very important. So let's look at an example that might make this clear. So say we are discussing which political parties are going to vote for this bill, right? So we've got three political parties. We'll say that we're in the American Congress. So we've got the Democrats, we've got the Republicans, and then we've got the Independents. We'll say that this is the set S for set. Okay, so we want to know what the power set of S is, and the power set of S, which is curly P, S, will be all the possible combinations of these three political groups. And this will give us an idea of all the possible voting bodies that could vote for our bill. The very first possibility is that all three of these political groups vote for the bill. Maybe it's just a very uncontroversial bill and, everyone passes it sort of ceremoniously. There's no disagreement. All three political groups vote for the bill. That's one possibility. Another possibility is it's everyone but the Democrats. So the Republicans and Independents. Another possibility, it could be everyone but the Republicans. And a final possibility, it could be everyone but the Independents. Another possibility, it could just be the Republicans. It could just be the Democrats. And it could just be the Independents. And the final possibility is that no one votes for the bill at all. So we just get the empty set. So this would be the power set of S, a power set of a 3-element set. We get this big set here. So it's a set of sets, and with 3 elements in the original set, we get 1, 2, 3, 4, 5, 6, 7, 8 elements in the power set. Let's look at another application of power sets. So if you've ever studied something like graphic design or image manipulation, you'll know that pixels, they have R, G, B values, which stands for red, green, and blue. So in this system, when we want to produce any kind of color, we have a particular level of red, a particular level of green, and a particular level of blue, which the pixel displays. Okay, so let's simplify the system a little bit and say that we can only have the max level of a color, like red, or the minimum level of a color. Now, that's not actually true in real life. In real life application of computer graphics, we can have many variations between the maximum and minimum amounts, but let's just simplify things for now and say that we can either have the maximum or minimum. So what I want to do is anytime we have the maximum level of R or G or B, we will represent it like this. So let's say that we have the maximum level of R and B, but the minimum level of G. We will represent it by just saying that we have R and B in our set. Given this kind of system, let's see what kinds of colors we can produce by looking at the power set of this set. The set of R, G, and B. Okay, so here we have 8 colors, and that makes sense because remember in our last example where our original set had 3 elements, the power set had 8 elements, so it's the same principle here. Okay, so we're looking for the power set of R, G, and B. So here, if we have the max levels of R, G, and B, we get white. If we alternatively have the minimum levels of R, G, and B, we get black. Now, these ones should be pretty clear as well. This is when we have the max level of R, but the min level of G and B, we get red. Likewise, we get green if we have just the max level of green, and we get blue if we just have the max level of blue. These ones are a little more interesting when we have no red, but just green and blue. We get this kind of aquamarine color or cyan. If we have no green, but just red and blue, we get this sort of magenta color. It looks a bit purpley, a bit pinky purple. And when we have no blue, we just have red and green, we get this kind of yellow color. So if we're just considering the minimum and maximum levels of the red, green, and blue values in a pixel, and these sets represent when we have the max level of color in that pixel, we get these 8 colors. So you could think of these 8 colors as representing the power set of our original set R, G, B. So let's go through an example problem, the kind of problem that you might see in an assignment. So we have 2 sets, A and B, and we want to find the power set of their intersection and the power set of their union. So let's figure out what their intersection is first. So A intersect B. So this would be the set of things that are in both sets. So I can only see 2. So it will be the set containing 2. Okay, so what would the power set of this be? So we just have a set with 1 element. So curly P, A intersect B. One guaranteed element of a power set is the set itself, because every set is a subset of itself. The set itself will always be one of the members of the power set. Likewise, the empty set will always be a member of the power set, because if you remember from a previous video, the empty set is a subset of every set. So here in this instance, we have what's called a singleton set, a set with just 1 member in it. The power set ends up just containing 2 members, the set itself and the empty set. Okay, let's look at the next one. So A union B equals, so it's going to be the set of all elements which are in either set. Let's just scroll up to look at what they are. So we got 1, 2, and 3. We don't need to count 2 twice. So 1, 2, 3. Now we've already seen what a power set of a 3-element set looks like, but let's quickly go through this one. So we know how many members it will have, right? It will have 8. Okay, so we've seen the general shape of the power set of a set with 3 elements. So we know that it contains itself because every set is a subset of itself. Likewise, we know it contains the empty set because the empty set is a subset of every set. Next, it will contain the sets of 2 elements, which are just missing 1 element. So this is the one missing 3. We'll do the one missing 2. And this is the one missing 1. Then we have the singleton sets. 1, 2, 3. Okay, so it's the power set of a set with 3 elements containing all 8 possible subsets. Okay, so you might have been noticing a pattern. Let's say we had a set with 1 element. Let's call it A. The power set of A contains 2 elements, the set itself and the empty set. If we have a set of 2 elements, A, B, the power set of B will contain 4 elements. So we got the set itself, as always, we got the empty set as always, and then we got the singleton set, so the set containing A and the set containing B. And then we've seen this a few times now, so I won't draw out the whole set. When we have 3 elements in the original set, the power set will have 8 elements, and we've seen that already. So if the original set has 1 element, the power set has 2 elements. If the original set has 2 elements, the power set has 4 elements. If the original set has 3 elements, the power set has 8 elements. Okay, so you might be noticing a pattern. The generalization is, if the original set has X elements, the power set has 2 to the power of X. For example, if we have 3, the power set has 2 to the power of 3, which is 8. If we have 15 elements, the cardinality of the power set, 2 to the 15th power elements, which is 32, 7, 6, 8 elements. There's a very interesting connection we can make here with binary numbers. So let's have a look at that. Here are the first 8 decimal numbers. So 0, 1, 2, 3, 4, 5, 6, 7. The first 8 if we're starting at 0. And here are the first 8 binary numbers. Now, if you don't know binary numbers, stay tuned. I might do a video about that. But just take my word for it that these are the first 8 binary numbers. Let's try to see the connection here to set theory. So let's go back to our old example of the Republicans, Democrats, and independents. So we've got Republicans, Democrats, independents. Now, let's say that when we have the Republicans, we put 1 as the left numeral. When we have the Democrats, we put a 1 as the middle numeral. And when we have the independents, we put the 1 as the right numeral. Okay, so let's try to find the correspondence between these binary numbers and the subsets of our original set, Republicans, Democrats, and independents. So here we have 0, 0, 0. We don't have a 1 anywhere, so this would be the empty set. Okay, here we have a 1 as the right numeral, so this would just be the independents. Here we have a 1 as the middle numeral, so this would just be the Democrats. Here we have a 1 as the middle and right numeral, so this would be the Democrats and the independents. Here we have a 1 as the left numeral, so this would be just the Republicans. Here we have a 1 as the left and right numeral, so this would be the Republicans and the independents. Here we have 1 as left and middle, so this would be Republicans and Democrats. And here we have 1, 1, 1, so this would be the full set. Okay, so you can see that what we've done, we've recreated the power set of our original 3-element set of Republicans, Democrats, and independents. Okay, so what we can see is that the binary numerals here are going through every possibility of having a 0 and 1 in each of the 3 possible positions. And we can see that when we do that, we end up with 1, 2, 3, 4, 5, 6, 7, 8 numerals. So say we want to generalize this, say that we want to figure out how many elements are in the power set of a set with 15 members, all we need to do is start at 0 and then go all the way up to the number with 15 ones, right? Now, this will invariably be the 2 to the 15th numeral, provided that we start at 0. Just like the binary number comprised by 3 ones is the 8th or the 2 to the 3rd numeral if we start at 0. Say we're investigating the power set of a set with 3 elements, like we are here. All we need to do is count from 0 up until the binary number comprised of 3 ones. Now, that will invariably be 2 to the 3rd or 8th binary number. So between 000 and 111, we will get every combination of 0 and 1 in 3 possible slots. So there's an exact correspondence between those binary numbers and the power set of a set with 3 elements. So this connection between the binary number system and power set operation should give you an understanding of why, if we have x elements in the original set, we have 2 to the x elements in the power set. Okay, here I'm just going to write down some really important things to remember about power sets. So we know that A is a subset of B means exactly the same thing as A is an element of the power set of B. So all the rules that we know hold for subsets also hold of power sets. So for example, A is always a subset of A, right? So every set is a subset of itself. So likewise, every set is an element of its own power set. Another rule that we have sort of talked about already, so the empty set is always a subset of any set, right? So the empty set is a subset of A for any A. So likewise, the empty set will always be an element of the power set of A. And, these rules just fall out of the intuition that being an element of the power set is just the same thing as being a subset. So the same rules should apply. Okay, what's next? Okay, so let's say that A equals the set containing 1 and 2. The power set of A, we should know by now, is the set containing 1 and 2. We always know that A is in the power set of A. The set containing 1, the set containing 2, and the empty set. Now, the next thing is, what if I take the union of everything in this set? So the union of everything in this set. Now, when I write union outside a pair of parentheses, all I mean is take the union of everything inside these brackets. So if I were to say the union of the power set of A equals, it would just be the union of all the component members. So 1. So for any set, no matter what the set is, the union of the power set of A for any set A always just ends up being A again. And you can kind of see that here, right? So A just contains 1 and 2. If we take the union of all these sets, we just get the set containing 1 and 2 again. Now we can also do this kind of notation with intersection. So what would the intersection of the power set of A be? Well, it would always be the empty set. Why would it always be the empty set? Because the empty set is always a member. So if we take an intersection of anything with the empty set, if we take any intersection with the empty set, we always end up with the empty set. Okay, let's look at another example problem. So this one is asking us, what is the power set of the empty set? Okay, so let's think about it. So the empty set is the set with no members. So the power set of the empty set would be the set of all its subsets. We know that the power set of a set A always contains A. So the power set of a set always contains that set itself. So it will contain the empty set. We also know that the empty set is a subset of every set. So the power set will contain the empty set. Now we know that repeats don't count. So we can just eliminate one of these. Let's eliminate that one. And we can just get the set containing the empty set. Okay, so the answer to that would be the set containing the empty set. Now we know from a previous video that the set containing the empty set is not the same thing as the empty set. These two things are different. Okay, the next question is asking us, what is the power set of that? So what is the power set of the answer to A? Okay, so we've already solved A, so we're a little bit ahead. Okay, so let me just scroll down. So we want to know B. What is the power set of the power set of the empty set. Okay, we know the power set of the empty set is the answer to A, which was this set containing the empty set. So what would this be? Okay, so we know, so we have a set which contains just one element. So there's just one element here. So this set will contain 2 to the 1 elements, or just 2, okay? We know the power set of A always contains A. So the power set of a set always contains that set, and we know it always contains the empty set, right? So we've got 1, 2 members, so that matches up with our intuition that the power set of a set with 1 element contains 2 elements. So this is our answer here. We just scroll up and write it in. Okay, so this one would be the set containing the empty set and the set containing the empty set. Okay, now question C is asking us what's the power set of that one. So it's asking us to go one step further. Okay, that's no problem, we can do that. Okay, so C is asking us what is the power set of the power set of the power set of the empty set. Dun, dun, dun. Now we know what the power set of the empty set is because we just worked it out. So it is the set containing the empty set and the set containing the empty set, right? Okay, so we want to know what this is. Okay, so it's a set with 2 elements. We know what that means. It should have 4 elements in the power set. So let's work out what they are. So we always know that the set itself is a member. So we've got the empty set and the set containing the empty set. We always know the empty set is a member. Then we've got the set containing just this member, which is the set containing the empty set, and the set containing just this member, which is the set containing the set containing the empty set. Okay, so that's the answer there. So we got 1, 2, 3, 4 members, which makes sense because this set has 2 members. So this set should have 2 to the 2, which is 4.
Okay, so that's about it for the concept of the power set. Let me know in the comments if you've got any more questions. I'll be happy to answer them. And I hope you all have a happy Halloween. Ooh. And I will see you next time. Bye, everybody.